from Asia A. Actually, the last speaker today.
Can you hear me? Yeah. Nice to meet you. I'm Sujin Eie from Asia A and NUJ in Japan. And I'm going to talk about our multi-frequency observations of radio magnetars and the cracked giant pulses. And as you know, this is the last talk, so I think you all will be very tired. So I'm going to finish as early as possible. So these are my collaborators, and I'm basically working on the people in Japan I had for the running observations using Japanese radio telescope. So let me start with the magnetars because, you know, as highlighted from many speakers during 2 days, for 2 days, we know that magnetars are really plausible, one of the plausible model of FRB. And we know we already have the galactic magnetar STR 9035, but still there are some FRBs that don't favor of the magnetar model. So I think you will agree that nothing will be the only model for FRB, but we will have a lot of models to explain the FRB emission, including magnetars. So, but the problem is that we know magnetar is important, but do you know that what is the radio emission features of magnetar is? And actually it is really difficult to understand because they are not well known, and also the lack of the observational results prohibit us to understand how they emit the radio emission. So as mentioned by Shotaro, the magnetars are defined with intense short burst pulsations and outbursts in X-ray and soft gamma ray. And so far, among the 3,000 radio pulsars, we have 31 magnetars that were detected by X-ray mainly. But among them, only a few magnetars are visible in radio, and the radio pulsations are also visible from 5 of the magnetars. So before moving on to the radio magnetars, let me shortly mention about the FRB and their spectral behaviors. And also, as highlighted by many speakers yesterday, FRBs are usually narrowband, and only one repeater, the FRB 201102, have ever detected at over 6 gigahertz. So, but unfortunately, there is no simultaneous detections of FRB at lower frequency. So we don't have a wideband spectrum of the FRB, and we don't know whether there will be a wideband spectrum of FRB, even though we have the simultaneous observations of FRB toward the repeating or non-repeating FRBs. So if I move on to the radio emission of the magnetar, I will call them as radio magnetars. And unlike the usual radio pulsars, they have very, very special characteristics. And I will gonna point out 3 things. And one thing is that their emission in radio is highly variable. The strong variations in many aspects, including profile and intensity and polarizations in time and frequency domain. And another one is that their radio spectrum is basically flat. So comparing to the average spectral index of standard pulsars as -1.6, magnetars are, if they are visible in radio band, their spectral index are around 0 or plus, or sometimes minus around 0.5. So it means that magnetars are easily detectable at high radio frequency. And you may know that one of the magnetars has been detected up to 300 gigahertz by JCMG recently. And one more thing that I want to mention is that their emission is transient. It means that they can be radio bright and can be radio quiet suddenly, that because of the unknown reason of their emission mechanism. So in this table, we can see the first column. I'm sorry that I cannot use my mouse, but the radio detection means that they haven't been detected in radio band, although we did a the monitoring of them after their X-ray emission has ever detected, but with unknown some mechanism in radio or their neutron star magnetosphere, suddenly their emissions start to be bright. But it doesn't mean that once the radio emission has started to be observable, we can see them for long. So this is the timeline of the magnetar radio emission so far, and you can see the white box and the yellow box that show that means that some of magnetars can be invisible after some period of the radio emission. So, and we don't know whether the other 4 magnetars, including the galactic magnetar, can be suddenly be quiet in radio band, and so we have to keep observing them to understand whether they will be gonna be undetectable in the future. So the radio turn-off mechanism of magnetars may be related to the long-term repeating timescale of FRB. This is my personal opinion, but we know some repeating FRBs can be visible after several months or several years, and maybe it could be applied to non-repeating FRB so far. And okay, so the reason that we started to observe the radio magnetars using our telescope is that basically the radio follow-ups are mostly being done at low frequency, because FRBs and radio pulsars are highly bright at low frequency around 1 gigahertz. But as I mentioned in the previous slide, their emission can be actually detectable at high frequency. But because of the variation, maybe we are gonna miss them if we don't observe them as soon as possible. So the prompt capture of the emission of radio magnetars at multi-frequency is highly important, and that's why we use these telescopes to study of them. And as Sota during the morning session explained about our Japanese facilities, these are the telescopes that we have ever used for pulse observations, and the frequency range that can be available for transient sources. And here in my talk, I will gonna mention about the radio magnetars and cracked ion pulses only, because FRB is already explained by Sota. Okay, so this is one of the results of the magnetars of XT1810, which was visible in 2017, and maybe it is still visible so far. So after the XT1810 started to be visible in radio, we do best follow-up observations from 300 megahertz to 22 gigahertz. So this is one of the results. And as you can see, it is not our first results, but we can see that there is some specific features in spectrum, including the kind of peak at 1 to 10 gigahertz, and another one that is marked with a pink color. So let me mention one by one. There should be the first one that is gigahertz peak spectrum. So in this figure, in the range that I marked with a blue shade region, we can see that there will be some kind of, in a day we can see one, but from also another day we can estimate that there will be a spectral peak, right? And this is called as the gigahertz peak spectrum, GPS. And it is not the only characteristic of radio magnetars, because we actually can see this GPS feature from 10% of the standard radio pulsars. And it is, we don't have a fixed model to explain the GPS feature, but the most plausible model of the GPS is the thermal free absorption by the electron matter surrounding the neutron star. So as you can see in the figure on the right side, we can test where the peak will appear depending on the temperature and the density and the thickness of the surrounding material. So maybe the surrounding material could be pulsar wind nebula or supernova remnant or something that we don't know. So if I move enlarge, mention one model result of the pulsar wind nebula from the simulation, then we can see that depending on the direction of the line of sight, the peak of the GPS feature can be changed. So we still have to do more observations of the magnetars to understand where there will be a pulsar wind nebula or something remnant or material that can explain the GPS features. And another thing is that in the area that I marked with a pink color, we can also see there will be another turn up in the spectral feature to explain, to connect our 28 gigahertz detection and the 100 gigahertz detection. So this is a kind of new idea for magnetars because recently also another 2 radio magnetars have been reported to have a turn up in their high frequency radio frequency region. So, but considering that the magnetar is still highly visible, only simultaneous measurements can confirm the presence of the turn up at millimeter wavelengths. So there is no model to explain, or because it was recently suggested. So it'd be great if you are to discuss with me together if you have any idea to think about the high frequency emission of the magnetar. Okay, and I'm sorry I'm spending a lot of time, but I want to mention another thing of the single pulse of magnetar, because we do have a lot of samples of the single pulse of the radio magnetar of XD1810, but from our 6 months observations, we didn't get any giant pulses. But after our observations finished, the low frequency at 1 gigahertz observation has got some samples of the giant pulse, but they didn't do the observations at other high frequencies, so we don't have the any spectrum of the giant pulse of the magnetar. So instead, we tried to compare the single pulse spectra of the magnetar and CRET GRP, and as you can see, the magnetar single pulses tend to be located at positive spectral index, unlike the giant pulses from the CRET pulsar at 2 to 8 gigahertz tend to be located at negative spectral index area. Okay. So as you know, still FRB is a narrow band, so we don't have any samples to explain, or any samples at including up to 8 gigahertz. So we only have the upper limit. But if we compare the spectra of the magnetars and the CRET pulsar and the known FRB upper limits, then as the lady mentioned, highlighted by Sota previously, we think that the giant pulse from the CRET pulsar may be still a little more favorable to explain the FRB spectral features. But you know that our observation, it was conducted during the early phase, so we still need more observations to explain, get more giant samples from the magnetar in wideband. Okay. So I'm sorry that I prepared too much things. So let me move on to, let me highlight one more thing that, still our samples, our data doesn't favor, our magnetar samples doesn't favor the FRB upper limit, spectral index upper limit, but still the magnetar FRB connections are really strong, because as you know that some FRB have the periodic subburst features, as we can see from the time result, and actually one magnetar have the subperiodicity in the burst. That is the only sample among the radio pulsar, and maybe the oscillations of the neutron star crust can explain both of them and support the connection of the two sources. So it'd be great that we can do more observations together at wide frequency and collaborate with the people in Japan to study and get more multi-frequency samples of the FRB and magnetar and giant pulses in the future. Yeah, so sorry for the long talk, and thank you so much.
Okay, thank you, Sujin. Was there any quick question? And then maybe we can move on to the discussion. Online question? Okay.
Yes, online question from Sumo.
Can I go ahead?
Yeah, sure. Thank you.
Yeah, yeah, definitely interesting results. Are there any differences or trends in the X-ray behavior of these magnetars when they're radio loud compared to when they're radio quiet?
Usually the radio outburst of the magnetar is accompanied by X-ray outburst, but I think there will be some specialties, but I'm really sorry, but I'm not very familiar with the X-ray outburst, so maybe Kunihito, can you, do you know?
Well, I was asking because at least for the particular burst, X-ray burst associated with the galactic FRB, they had an atypical spectrum which was hard and non-thermal-like, which is different from the normal X-ray burst, and I was wondering whether there might be some differences in the X-ray behavior of these radio loud phases and compared to radio quiet. But okay, maybe.
Yeah. Right.
Maybe
We still
something-
have only 2 samples that was detected with a radio outburst from this
Okay.
magnetar and another one, SGR 1935. So, yeah, I'm sorry, but maybe we need more the further observations to compare the X-ray.
I guess Susumu is
okay.
asking about maybe magnetar. Was there any magnetar flare activity during this observation, radio observation?
During our observations.
Yeah.
No.
No.
Oh, yeah.
Oh, okay,
the
okay.
flare was.
My question was more general.
Okay, okay.
I'm sorry. Yeah.
Okay, thank you.
Thank you so much.
Let's thank again the speaker.